If you've been following the rapid evolution of LLM-based agents, you know that deep research systems are quickly moving from conversational assistants to autonomous, long-horizon information-seeking engines. They decompose complex queries, run iterative search loops, accumulate intermediate analyses, and synthesize structured reports. But there's a critical question that hasn't been thoroughly answered. When these agents ingest seemingly credible but factually false information, do they actually adopt those false conclusions in their final output? A recent paper from researchers at the Shanghai Artificial Intelligence Laboratory and Beijing University of Posts and Telecommunications tackles this directly. Titled "Is Deep Research Reliable? Misleading Knowledge Induces False Conclusions." The study introduces a controlled evaluation framework called MisKnow-Agent, and the results reveal a highly systemic vulnerability in how these agents handle evidence compression and synthesis. Let's break down the methodology, the technical findings, and what this means for the architecture of next-generation research agents. The core problem stems from how deep research workflows actually operate. Unlike short-form retrieval-augmented generation, where retrieved context is typically used to draft a direct answer, deep research agents operate over extended life cycles. They plan, search, read, analyze, and synthesize. Misleading content doesn't need to be injected at the very beginning. It can surface during mid-research retrieval, get compressed into intermediate memory states, and later be reused during final synthesis without explicit verification. The threat model here isn't a targeted adversarial attack or prompt injection. It's an ambient reliability risk. The fact that open web research environments naturally contain outdated, weakly supported, or fabricated content that can look perfectly legitimate. To isolate this failure mode, the authors built MisKnow-Agent. The framework constructs task-specific misleading documents with tightly controlled variables. For each research query, it generates a blueprint that defines a canonical false conclusion, an institutional authority pool stratified into high, medium, and low tiers, and clear evaluation criteria for adoption. From there, it generates documents across different presentation styles: academic paper, news article, technical blog, and social post. Crucially, writing quality, coherence, and retrieval friendliness are held constant across all tiers. The only signals that vary are the source metadata, institutional authority cues, and stylistic formatting. To ensure these documents are actually misleading, and not just ambiguous or unverifiable, the framework runs a search-guided refinement loop. 5 independent, search-enabled verifier models evaluate each candidate. A document is only retained if all verifiers consistently classify it as factually false. If even one verifier finds corroboration, the document is refined or discarded. After cross-model verification and manual screening, they produced 5,933 quality-controlled misleading knowledge instances mapped to tasks from the deep research bench. Now, how do they measure failure? They use the false conclusion adoption rate, or FCAR. This isn't a simple mention metric. A report only counts as an adoption if it endorses the seeded false conclusion as its own factual answer in the final synthesis. Mere quotation, attribution, uncertainty, or explicit refutation does not count. This distinction is critical because it isolates whether the agent's reasoning pipeline actually internalized the false premise. The experiments were run across 2 open-source frameworks, DeerFlow and WebThinker, paired with 3 backbone LLMs, Intern S1 Pro QN3, 5-397B, and DeepSeek V4 Pro. They also evaluated Gemini Deep Research as a closed-source baseline. The baseline condition, with 0 injected misleading documents, yielded a 0% FCAR across all configurations. The systems simply don't hallucinate these specific task-level false conclusions on their own, but introduce a single misleading document, and the mean FCAR jumps to 54.7%. Let's look at what drives that adoption rate. First, search result rank has surprisingly little influence. Whether the misleading document appeared at the top, middle, or bottom of a search result list, adoption rates hovered around 65% across all configurations. This tells us that agents are relying heavily on content relevance and semantic alignment, rather than list position as a trust signal. What matters significantly more is lifecycle stage. The researchers varied exactly when the misleading knowledge entered the workflow. When injected at cold start, FCAR was around 40%. During mid-research retrieval, it stayed near 44%. But when introduced immediately before the final synthesis phase, adoption spiked to 85.5%. The reason is architectural. Once an agent transitions from evidence gathering to synthesis, it begins compressing, summarizing, and structuring information. If false evidence is present at that stage, it gets baked into the narrative with minimal opportunity for cross-checking or displacement. Next, let's talk about source cues. Authority matters, but presentation style is a stronger and more consistent predictor of adoption. High-authority sources yielded a 61% FCAR, medium dropped to 57.7%, and low to 46.2%. But style differences were even starker. Paper-style documents drove the highest adoption at 61%. Blogs followed at 53%, news at 44%, and social posts at 37.5%. The gap between paper and post is actually larger than the gap between high and low authority. This makes sense technically. Academic formatting, methodological hedging, and structured citations trigger stronger trust priors in reasoning-heavy models, especially when those models are optimizing for technical coherence and domain alignment. The framework and backbone model interaction reveals another nuanced failure mode. DeerFlow uses a relatively direct planner-researcher-reporter pipeline. Queries stay close to the original task, and retrieved documents are preserved in the researcher's observations before being passed to the reporter. WebThinker, on the other hand, decomposes tasks into finer-grained subqueries, compresses retrieved evidence into document memory, and drafts the report section by section. You might assume that compression and subtask decomposition would naturally filter out false evidence. And in some configurations, it does. WebThinker showed lower adoption at cold start and mid-research. But that advantage reversed during pre-synthesis, and overall FCAR still ranged from 50 to 76%, depending on the LLM. Here's where it gets technically interesting. The researchers introduced two metrics to decompose the framework gap: misleading evidence reach, which measures whether the agent actually retrieved at least one injected document, and exposure conditional adoption rate, which measures adoption given that retrieval occurred. The data shows that framework differences aren't just about retrieval capability. They're about conditional adoption. For example, Intern S1 Pro under DeerFlow had high reach and high conditional adoption, while QN3 5-397B under WebThinker had near-perfect reach but lower conditional adoption. This proves that robustness isn't a property of the model or the framework alone. It's a joint property of how a specific LLM processes, retains, and weights evidence within a specific architectural pipeline. What about defenses? The authors tested two complementary approaches. The pre-research defense appends a verification-enhanced prompt before the workflow begins, instructing the agent to treat all retrieved information as unverified until corroborated by primary or independent sources, and to qualify or omit claims backed by weak or conflicting evidence. The post-research defense introduces a separate refinement agent after the initial report is generated. This agent iterates through the final report claim by claim, retrieves independent evidence using the same augmented retrieval environment, and corrects or qualifies unsupported claims while preserving the original structure. Both defenses reduce FCAR, but neither eliminates it. Pre-research drops adoption to a 37 to 57% range. Post-research brings it down to 20 to 58%. Combining them doesn't always yield additive gains. In fact, for Intern S1 Pro, the combined defense performed worse than either defense alone. The reason is structural. The post-research refinement agent operates in the exact same contaminated retrieval environment as the original research process. It can re-retrieve the same misleading documents, and without explicit cross-state verification, it can inadvertently validate the false premises it's trying to correct. The broader implication is clear. Identifying misleading documents in isolation is insufficient. Verification and correction need to be integrated continuously across intermediate research states, not just bolted on at the beginning or end of a pipeline. Evidence handling in long-horizon agents requires state-aware auditing, cross-temporal consistency checks, and explicit confidence calibration that survives evidence compression. This research provides a highly reproducible benchmark for evaluating deep research reliability. The MisKnow-Agent framework, along with the 5,933 controlled instances, is publicly available for researchers to stress-test their pipelines. More importantly, it shifts the conversation from whether agents can answer complex questions to whether they can maintain evidential integrity when the information environment itself is noisy, fabricated, or strategically misleading. If you're building or evaluating long-horizon research agents, this paper should be on your reading list. The failure modes it identifies aren't edge cases. They're inherent to how iterative synthesis and evidence compression currently work. Continuous verification, state-level tracking, and architecture-aware defense strategies will be necessary to make these systems truly reliable in open web environments. Check out the paper and the open source code and dataset if you want to dive into the full methodology, prompt templates, and evaluation pipelines. And if you're interested in the latest research on agent reliability, retrieval robustness, and long-horizon reasoning, make sure to follow along as we break down more of these papers. Thanks for watching,